Greetings A-level chemists, welcome to Required Practical 10 for the AQA specification. We're preparing an organic liquid. So it's a variation on a theme. Most important part of this is looking at our experimental techniques and why we do what we do. So just to put this into context, we are dehydrating an alcohol to form an alkene. So we're starting off with cyclohexanol. So this is cyclohexanol. I've done it as the boat configuration. You don't need to do it as that. I just thought it looks nicer. So you could do it as this. That's absolutely fine, okay? And then what's happening is with an acid catalyst, what's happening is we're protonating. So we're protonating this oxygen to make it a better leaving group. So if we've got some H plus coming from the acid catalyst, what happens there is we protonate that to get OH2 plus, and then we get the OH2, so the water leaving, so we're dehydrating it because we're removing water, and then we're forming a CC double bond. So what we're doing is we're going from this to this plus H2O with an acid catalyst. Okay, cool. So that's the context. So this is elimination or dehydration. Okay, so what I'll do is I'll just get rid of that and annotate that as cyclohexene. So the cyclohexanol has a higher boiling point than the cyclohexene because of the hydrogen bonding in cyclohexanol that we don't see in cyclohexene. Okay, so they've got the cyclohexanol, they put it into a round bottom flask, there we go, and 3 centimeters cubed of conc phosphoric acid was also added to the flask. They added some anti-bumping granules, so they added a few anti-bumping granules, and then what else did they do? And then they set up the equipment as shown in the figure below. So this is distillation. So then they heated the mixture. So they heat the mixture and then collected the liquid that distilled at temperatures below 100 degrees C. All right, cool. So what's going on here then? They've got a heat source. They've got some anti-bumping granules in here and they're heating it up, and the vapor that comes off when the temperature reads 100 degrees C, sorry, below 100 degrees C, that's the vapor that's going to be collected. All right, cool. So then let's just think about distillation. So water in through the bottom, water out through the top. So this has to be closed here. So this has to be closed so the vapor hits that thermometer. The thermometer should be in line with the condenser as well. So you're collecting the temperature of the vapor that you want to collect. And then it's going to trickle down. And remember, this needs to be covered in water. So the jacket of the condenser should contain water. And if we set it up properly, then it should cover all of the condenser. Okay, so there shouldn't be any gaps. That's why we set it up in a countercurrent mechanism or countercurrent flow, so the water goes in through the bottom, out through the top, so that all of the condenser jacket is full up with water. So then the vapor that's coming off, once it hits the cold surface, it cools and condenses and then trickles down as a liquid, and the distillate is collected here. So then once we've got the distillate, we're going to place it into a separating funnel and we're going to wash it with sodium carbonate. So what I'm thinking here is the sodium carbonate, which is a base, is going to be reacting with any H3PO4 that was left over. And if it reacts with the acid, we're going to be making CO2. So periodically, we're going to have to invert the separating funnel and open the tap. So then we're going to get 2 layers forming. So we're going to get 2 layers forming in the separating funnel. So we need to dry the final organic product using anhydrous calcium chloride, which is a drying agent. So it'll just take in the water. So then after drying the product, the drying agent is removed by filtration under reduced pressure, i.e. Buchner funnel attached to a pump. Okay, cool. Right, so let's have a look at the question in a little bit more detail. So, the student collects 5.97 grams of cyclohexene in the experiment. Determine the percentage yield of cyclohexene. Okay, cool. So I guess where do we go first? So let's think about what we could do. So we've got the density of cyclohexanol. Okay, I might work backwards. Let's see how it goes. So I've got the mass of cyclohexene. So I'm going to work out the number of moles of cyclohexene actually. So these are the number of moles that I actually get. All right. So we'll start here. We'll start backwards because why not? It's as good a place as any. So the number of moles is going to be 5.97 grams over the MR, which is 82. So you should get 0.0728 moles of the cyclohexene. So then where do we go next? So we could work out the number of moles of cyclohexanol. Okay, to work out the number of moles of cyclohexanol, we have to use the relationship for density, mass, and volume. So density equals mass over volume. So that means that the mass is going to be equal to the density multiplied by the volume. So that's going to be step 1 of part 2 in this calculation. So the mass of cyclohexanol used is going to be 0.96, which is the density, times the volume, which is 10. So it's going to be 9.6 grams. So then I'm going to work out the number of moles of cyclohexanol used. The number of moles is going to be equal to the mass that I've just worked out, which is 9.6 over 100. So that is 0.096 mole of cyclohexanol used. So then let's look at this relationship. So I've got the number of moles of cyclohexanol used. It's 1 to 1, so I can work out theoretically the number of moles of cyclohexene that I could have made. So then, number of moles of cyclohexene, and this is theoretical. Okay, if I've got the number of moles of cyclohexene, which is theoretical, that's going to be 1 to 1. So therefore 0.096 moles I could have theoretically made. So then I'm going to work out the mass of cyclohexene that I theoretically could have made. I'm just going to call it Theo. So that's going to be the number of moles that I theoretically make multiplied by the MR, which is 82. So that gives me a theoretical mass of 7.872 grams. Okay, so I've got the theoretical mass and I've got the actual mass as well. So now I can work out the percentage yield, and it's trivial. So percentage yield equals my actual mass, which is 5.97, over my theoretical mass, which is what? 7.872 multiplied by 100. So I could have done it from the moles, really. I could have done it from the moles. Hence working out step 1. Didn't even need to do that bit, but we've done it anyway, so why not? So multiply that by 100. I should get 75.8%. So let's just call that 76%. Okay. Alternative way, what I could have done is I had the actual number of moles. So I could have used 0.0728 over the theoretical number of moles that I should have got, and presumably this gives you the same value. And yes, it does. So it gives you 75.8. So I could have, if I wanted to, I could have stopped there, really. I could have stopped there and actually gone up to here, and I could have used my moles. There you go, 2 different ways of getting to the same answer. Okay, next question. Describe a test tube reaction that you could do onto the product to confirm that all of the cyclohexanol had undergone dehydration. Okay, so here's my cyclohexanol, and when we dehydrate it, we're forming cyclohexene plus H2O. So a test tube reaction to confirm that all the cyclohexanol had undergone dehydration, or at least undergone some dehydration, we'd add bromine water. Because bromine water should react where that double bond is, and we can say that the bromine water will decolorize. And bromine water, and it will decolorize, i.e. go from orange to colorless. Okay, next question. Explain why sodium carbonate was used to wash the distillate. Okay, so we've got the distillate in here, and I'm adding sodium carbonate, okay? So what is the point of adding sodium carbonate? Well, we said it is a weak base, and this is going to react or remove any phosphoric acid used for the dehydration. So to react or remove any H3PO4 used for dehydration. That's it. Okay, and then let's think about what's happening. Why do we need to open the separating funnel periodically? So we've got some sodium carbonate in here, and we've got our organic liquid. Now, it's likely that that's going to be the organic phase, if it's got a lower density. So if this is our aqueous phase, which is more dense, it's going to form at the bottom. So what happens is we've got our sodium carbonate in here, and we've got some leftover H3PO4. So let's say we've got some leftover H3PO4 and we've got some sodium carbonate. So these guys, when they react, they're going to form CO2. So when CO2 builds up, the pressure is going to build up. So what we do is we invert the separating funnel, okay? So that literally means is we flip it. So once we flipped it, I inverted it, turned it upside down, and then we opened the tap. So we can see that the tap is open when it's in line with that spout, okay? So it's closed in this orientation when it's at 90 degrees to the spout. So then what's going to happen is, now I've opened it, the pressure that built up due to the CO2 is now going to be relieved as the CO2 escapes. So that's why we periodically invert it and then open the tap to remove any CO2 that builds up due to the reaction with sodium carbonate. Okay, so that is why we do that. So let's just write a response to this. So we do this to relieve or reduce the pressure buildup due to CO2 or from CO2. And you don't need to put this next bit in, but it's really handy to know this reaction. So here's my carbonate ion. Here are my H+ ions from the phosphoric acid, making H2O liquid and CO2 gas. So this is from my sodium carbonate, and this is from my H3PO4. So this we're removing, and this is going to be part of my aqueous phase. Okay, cool, nice question. Where do we go next? So state one property. So then what we're doing, I'll just quickly go back to this slide. So what we're doing here is, once we've reacted all this stuff, we're going to open the tap, and this aqueous phase we're going to collect. Okay, so once we collect the aqueous phase, we're just going to discard it because we're interested in the organic liquid, right? So then we should have isolated our organic liquid, which is in here. So then we isolate our organic liquid by closing the tap really quickly and then stop. We're just going to collect that bit, okay, when we discard the aqueous phase. Okay, so once we've collected our organic phase, there might be some water in there still. So what we do is we then then we add some anhydrous calcium chloride, which absorbs water, so it's acting like a drying agent. But another reason for using anhydrous calcium chloride is it's inert, or it doesn't react with cyclohexene, which is what we're collecting. We don't want it to react with the cyclohexene because we're collecting the cyclohexene. Okay, then next step. We've got to explain the equipment used to remove the drying agent by filtration under reduced pressure. So we can do it in terms of a labeled diagram. That's what I would choose. So here we've got a Buchner funnel. So this is a Buchner funnel. And here we've got our filter paper. So here we've got our filter paper, okay? And then we attach the Buchner funnel to a conical flask with a sidearm, and that is attached to a vacuum or a pump. Now you don't have to draw it like this, but that's how it's going to work. Now your diagram has to be pretty good in that there should be an airtight seal between the Buchner funnel and the conical flask. Okay, if it's open, then it's not going to pull a vacuum, and you're defeating the object of using a Buchner funnel. You might as well just filter under gravity in that sense. So where are the marks actually coming from? So you need to have a Buchner funnel. So it needs to be flat, and the perforations are showing the filter paper here. So just annotate this with a line, and that's your filter paper in red. There it is. And what happens is the filter paper catches any solid impurities, and then the perforations allow the liquid to go through. That's in the Buchner funnel. And then the Buchner flask, or simply a conical flask with a sidearm, that is connected to a vacuum pump. So this is my Buchner flask with sidearm connected to pump. And remember, we're interested in the cyclohexene, okay? So we're interested in the stuff that we get in the conical flask, okay, not the stuff that we're collecting in here, because that's just the crud. Okay, and then we find out that a sample of cyclohexene has been contaminated with cyclohexanol. Uh-oh. The two compounds can be separated by column chromatography, and we use silica gel as the stationary phase and hexane as the mobile phase. Explain why cyclohexene has a shorter retention time compared to cyclohexanol. Now, it might think, oh God, I didn't do column chromatography, we didn't cover it in school. Well, actually, we can get away without knowing too much about column chromatography, okay? So the first thing we have to say is that cyclohexene is less polar than cyclohexanol. Remember that in cyclohexanol we have an OH group, and in cyclohexene we don't have that OH group, okay? So cyclohexene is more soluble. It's more soluble in hexane, and hexane here is a non-polar solvent. So like dissolves like here is a good rule of thumb. So cyclohexene is more soluble in hexane than cyclohexanol. So we'll just add this in. So the cyclohexene has a stronger attraction to the mobile phase, i.e. the solvent. So move through the column, faster, and if something is faster, it has a lower time, right? Done. Okay. Last sub-question. We've got to explain how IR could be used to confirm that the cyclohexene collected from the column doesn't contain any cyclohexanol. Okay, so what we're looking for is an absence of this OH peak. Now this peak is going to occur around what, 30 to 3,550 inverse wave numbers. So if we're converting, or if it's not contaminated with that, then that peak should be absent. So we shouldn't see that peak there. So we're just going to say the absence of an OH stretch at 3230 or 3550 inverse wave numbers. And that's it. Okay, hope that was helpful. Thank you for watching. We'll call it time there. See you later.